All right, so calculus is all well and good, but let's get into calculus in physics. There are all kinds of wonderful ways that calculus comes up in physics. So let's first give a simple example. We've seen this idea, but I want to remind you that if you have a graph of velocity versus time, let's say time's in seconds and velocity is in meters per second, and we have this baboon, and over the period of 4 seconds, that baboon starts with a velocity, I'll put it in blue for you, the velocity is 0, and then it goes up to some value, stays there for a little bit, and then the baboon stops. The baboon stops, and so this value right here, we've got to name that. Let's say that it's 10 meters per second. What we could ask after showing you a graph like this is, how far has the baboon gone? And that's a simple calculus problem, because we know that displacement is the integral of velocity over time, dt. So we need to take the velocity and integrate it over time, and that means that we're just finding the area underneath this curve. So let's just look at it geometrically. This is a very simple problem. We have, well, I see a square right here, and I see 2 triangles there and there. So let's name these areas. I'm going to call this area 1, area 2, and area 3. This is 1 second, 2 seconds, 3 seconds, 4 seconds. So the area of area 1 is 1/2 base times height, and that's equal to, let's see, the base is 1 and the height is 10, so that's 5, and the units of the base is seconds, and the units of the height is meters per second, so we're going to 5 meters. Area 2 is base times height, so we've got 1 second times 10 meters per second, 10 meters, and area 3 corresponding to area 1, 1/2 base times height, also 5 meters. So we say the baboon went 20 meters. Yo, that's an easy problem, but we don't know where the baboon is. That's that initial conditions that we don't know. All we know is that it was displaced. So maybe we should change this to say the baboon was displaced by 20 meters. Yo, okay, so that's great. Well, we also know that change in velocity is the integral of acceleration over time. So we could do a problem that shows that. For instance, I could have a rocket, and the rocket might have an acceleration graph that looks like this. It might have a large acceleration. I'll put this in blue for you again. A large acceleration, and then gradually as the rocket burns out, the acceleration goes to 0. We'll deal with rockets, and this is probably not exactly accurate, but let's say that this happens over a period of 5 seconds, and the burn down takes another 3 seconds, so we're at 8 seconds right there. And let's say the acceleration, it's probably several G's. Let's say it's 10 G's, so we could call this about 100 meters per second squared. That was the acceleration initially. Whew. Then, excuse me. Wow. Maybe I'll edit that out. Maybe not. We know that since the change in velocity is the integral of the acceleration over time, all we have to do here is find the area. And I'm going to split this into 2 areas again. I hope that's kind of an obvious step for us. And my plan then is to look at area 1 and area 2. Area 1 is, let's see, base times height. The base is 5 seconds, and the height is 100 meters per second squared. We're multiplying that by seconds, so we're going to get something in meters per second, and the answer, of course, is 5 times 100, so that's 500 meters per second. This is going to be a fast-moving rocket. Area 2 is 1/2 base times height, so we've got a base of 3 seconds and a height of 100, so we'll get 300, then we have to divide that by 2, so we have 150 meters per second. And we can therefore conclude area total is area 1 plus area 2. We can therefore conclude that this is the change in velocity of the rocket, and that's 650 meters per second. So it's going that much faster than it was initially. But again, I should point that out, probably in blue, we don't know VI. The initial conditions, that constant that we have to add into the integral, is unknown, and that's all right. Another cool way that we can use calculus in physics problems is, and this is really a wonderful thing, there are some equations that may seem in the first year of physics completely unjustified. And we're going to justify those equations by calculus. You've seen one of them already. One cool equation that we justified was that final position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. So I hope that we'll justify a couple other equations that looked kind of weird to you the first time you saw them. We'll start out with forces, because we know that, well, last year I told you that work is force dot distance. So that means that work is done when a force acts in the direction that something moves. But this dot product, well, the dot product has a cosine in it. You want to put that on there? We can put it on here. Force times distance times cosine of the angle between force and distance. Put that. This is the angle between force and distance. So, for instance, this is a very important point. For instance, the magnetic force, QV cross B, that's the force on a charge moving in a magnetic field, that force can never do any work because it's a cross product, and so in fact, the force is always at a right angle to the velocity. So the force is always at a right angle also to the distance that the charge has traveled, and that force can never do any work. It can't change the energy of a charge that's moving in a magnetic field. But let's look at some forces that can. For instance, this equation is rather simplistic, so I'm going to be a little bit more careful with it, and I'm going to say, but actually, truly, work is the integral of force dotted in to distance. And I'm going to say dot dx. That's force integrated over distance. This is the best way to put it. Force integrated over the direction traveled. There's a dot product in here, but we're only going to consider, I only want to consider when force is parallel to dx. So we'll just have work is the integral of force over distance. All right, so we're going to take this equation and we're going to plug in some known forces and get some wonderful results. Work done in a system is often the energy stored in the system. So if there's no friction, we're going to find that the work done is the energy stored. So when we get answers like potential energy, I don't want you to be too surprised. So on the next sheet of paper, I'll start out by again saying work is the integral of force over distance. And let's consider the force of gravity first. near Earth, we've got the force of gravity is m times g, right? No problem. So let's take that and try to figure out the work done while lifting something. Lifting a boombox. Yeah, 1980s. Work done while lifting a boombox is the integral of that force while lifting the boombox over the distance that we've lifted the boombox. So let's do this integral. We're going to plug in what the force to lift the boombox is, and it is the integral. We'll still have an integral. It's m times g over distance. Does mass change as the boombox rises? No. Does baby g, that constant of nature, let's put up here, baby g as I define it, is 9.81 meters per second squared. That's the acceleration of gravity where I live, and so we'll use that. Does baby... Sorry about that squeaking, it's driving me crazy. Let's try that. Yeah? No? No? Okay. Baby g and m don't change as distance goes on, so we can pull them out of the integral. This is pretty fancy. M times g times the integral dx. But the integral dx is a little bit funny. I'm going to write it a little bit differently. We're going to have m times g times the integral of, well, you know, you could throw a 1 in wherever you want, right? This is the integral of 1 over distance. So as distance goes on, you add more and more distance. So let's see, the integral of 1 over distance is simply equal to x. Well, it's a constant also. But in this case, the constant is going to be 0. Okay, so we can just plug in x. This is m times g times the distance that we've lifted the boombox. You want to come up with a fancy letter for that? I was thinking I would put h there. Oh, snap. The work done by lifting a boombox is mgh. Let's see, potential energy gravitational is mgh. Okay, good, let's do some more. Sometimes I'll tell you that the force of gravity is, well, oftentimes I'll tell you it's g times m1 times m2 over r squared. Now this would be the case where you're not near Earth's surface. Something more interesting might be happening. So we can calculate the work done by the force of gravity in this case also. Let's see, this is the integral, I should title it first. Work done moving two large planets apart. The work done moving these two large planets apart is the integral of the force moving the planets over the distance that the planets have moved. So these two planets, let me draw a sketch of these two planets. One of them small and the other one's big, and they're separated by some distance that we can call r. That's the distance between the two planets. Maybe we could say it's the distance from that one to that one. It's the vector r. So instead of an x here, we'll want to put an r there. I think that's what I'll do. Also, I'm going to plug in what the force to move the planets is. It's this thing right here. Take it and plug it in right there. So I'm going to get, it is the integral of capital G times the mass of planet 1 times the mass of planet 2 divided by r. And remember, instead of saying x, I'm going to say we're actually moving them apart in that direction. So there is, let's see, there's a minus sign here in this force, isn't it? Yeah, that's an attractive force. I can put the minus sign right there. And we're integrating over r, as discussed. So let's put another equal sign down here. Does the universal constant of gravity change while we move apart two planets? Gee, I hope not. Does the mass of the planet change as we move them apart? No. The mass of the other planet? No. What about the distance between them? That should be squared. Notice I just changed that. Sorry, big mistake. That was squared up here. It should be squared right there. The distance between the two planets will be changing, so we have to leave that. And I'm going to leave this, well, I'm going to pull out the stuff, negative g times m1 times m2 over r, whoa. Oh, this is very sloppy. I'm terribly sorry. I've got negative g times m1 times m2 times the integral of 1 over r squared dr. This integral is simply the same thing as the integral of r to the negative 2 dr. And you know how to deal with r to any power, right? This, in fact, is simply, well, I guess we're going to raise the power of r. So I'm going to get r to the negative 1, and then I need to multiply it by the new power of r. No, I need to divide it by the new power of r. So this is r to the negative 1 divided by negative 1 plus some constant. But let's simplify this a little bit more. This is simply r to the negative 1. It's negative 1 over r plus a constant. Again, our constant's going to be 0. Okay, 0. So let's plug this in. I've got negative g times m1 times m2 divided by, well, there's another minus sign. See this minus sign right here? So we're going to make that a plus, divided by r, but not r squared. That right there. This is the work done while moving apart two large planets. G times m1 times m2 over r, not r squared. In fact, the potential energy, the gravitational potential energy between two large masses is capital G times m1 times m2 divided by r. And that's how we get it. Awesome, right? Let's keep going. What if you've got two charges? The electric force between two charges is Kc times Q1 times Q2 over r squared. You can bet, it's negative again, you can bet that this discussion will almost exactly parallel the previous discussion with gravity. Here we go. I'll set up the same picture in the upper right corner, and I'm going to have Q1 and Q2, Q1 and Q2. And I'm going to move those suckers. Let's see. I'm going to move them so that they are further apart. And I'm going to establish the r vector going that direction. What the heck, right? Work done moving apart two charges. That is the integral of the force to move charges integrated over the distance the charges have moved. But in the same way, we can plug in all this stuff. I'm going to plug in the force to move the charges, which is negative Kc times Q1 times Q2 over r squared. And then we're integrating over r because we're moving in a radial direction. That's nice. And this is equal to, let's see, I'm going to pull out all the constants. So in just the same way, I have negative Kc times Q1 times Q2 times the integral of 1 over r squared dr. This is the same thing as Kc, let's see, negative Kc Q1 Q2 times the integral of r to the negative 2 dr. So just as we had before, this integral is, well, it's not a complicated integral at all. It's simply going to be negative 1 over r plus a constant, but I want that constant to be 0 again. That's what it is. Why there's 0 is a little bit of a subtler thing, and we can talk about that later. Ask me in class, send a note to the comments, etc. But we can simply plug in negative 1 over r. So the r's are going to, sorry, the minus signs are going to cancel, and we'll have Kc times Q1 times Q2 over 1 power of r because this integral gave us 1 over r, minus signs canceled, and there we are. That's the work done to move apart two charges. It's also equal to electric potential energy between two charges, Kc Q1 Q2 over regular r. Look at that. Not only that, but I think we should point out that this energy is positive if the charges have the same sign. That doesn't make sense. We probably move them opposite directions. So I'm going to put a minus sign in front of this. The energy should be negative if they have the same sign. So I'll put a minus sign right there. And that came from this right here. If we were moving them apart, then that's opposite the direction of the force. So I need to put a plus sign right here. We can trace that all the way through. We could talk about that in class. I understand that's probably pretty confusing. So I'll just have a minus sign right there. Okay, very good. So this is the electric potential energy when two charges are separated. It is negative when the charges have the same sign, and it's positive when the charges have opposite sign. That makes sense because as charges move apart that have opposite sign, that system gains energy. If charges have the same sign and they move further apart, then that system's losing energy. Think about it this way. Charges with the same sign that are moving apart will be speeding up. So they'll be losing potential and gaining kinetic. All right, I have one final thing to share with you, and this is probably my favorite application of calculus to physics: springs. So the work to compress a spring, the force of a spring, often called the elastic force, is negative k times x. And I'm going to talk about the work to compress a spring. Well, it'll be the work to compress or stretch a spring. Is the integral of the force of the spring over how far we have moved that spring. So let's plug this in very carefully. If I'm moving the spring this way, then the force points this way. So we're actually going to get another minus sign when we put this into here because of the dot product. Can I wave my hands at that? All right, so I'm going to plug this in. Negative kx times dx times minus 1 because of that dot product, the cosine. You could say it's a cosine of 180 if you want. Anyway, this simplifies to simply the integral of kx over x. And again, one of these things is not changing as x changes. This right here is just the instructions. This is called the integrand. That's what's actually being integrated. So this says integrate, and this says over x, and then that's what we're actually integrating, k times x. So the k pulls out, because it is, as you guessed, a constant, k times x dx. And the integral of x is simply x squared over 2. Well, plus a constant, right? We've got this, sorry, I'm going to have to take this. This integral right here is a known integral. It's very simple. X squared over 2 plus c. And c is 0. Again, so we're going to be able to plug this in as k times x squared over 2, which written another way is 1/2 kx squared. Ever seen that before? I think you have. The work done to compress or stretch a spring, 1/2 kx squared. This is also the elastic potential energy of a spring. It is simply 1/2 kx squared. And that's true if there's no friction internal to the spring. Most springs, when you stretch or compress them, heat up a little bit. You can tell that with a rubber band. It's very fascinating. Do a rubber band a few times, put it to your cheek. It's kind of hot. I didn't mean it like that, but it is a high temperature. Okie dokie, that's all I've got for today. Yes, it might have a large acceleration. I'll put this in blue for you again. A large acceleration, and then gradually as the rocket burns out, the acceleration goes to 0. This is, we'll deal with rockets, and this is probably not exactly accurate, but let's say that this happens over a period of 5 seconds, and the burn down takes another 3 seconds, so we're at 8 seconds right there. And let's say the acceleration, ooh, you know, it's probably several G's. Let's say it's 10 G's, so we could call this about 100 meters per second squared. That was the acceleration initially. Whew. Then, excuse me. Wow. Maybe I'll edit that out. Maybe not. We know that since the change in velocity is the integral of the acceleration over time, all we have to do here is find the area. Then the balloon, the baboon stops. The baboon stops, and so this value right here, we've got to name that. Let's say that it's 10 meters per second. What we could ask after showing you a graph like this is, how far has the baboon gone? And that's a simple calculus problem, because we know that displacement is the integral of velocity over time, dt. So we need to take the velocity and integrate it over time, and that means that we're just finding the area underneath this curve. So let's just look at it geometrically. This is a very simple problem. We have, well, I see a square right here, and I see two triangles there and there. So let's name these areas. I'm going to call this area 1, area 2, and area 3. This is 1 second, 2 seconds, 3 seconds, 4 seconds. So the area of area 1 is 1/2 base times height, and that's equal to, let's see, the base is 1 and the height is 10, so that's 5, and the units of the base is seconds, and the units of the height is meters per second, so we're going to 5 meters. Area 2 is base times height, so we've got 1 second times 10 meters per second, 10 meters, and area 3 corresponding to area 1, 1/2 base times height, also 5 meters. All right, so calculus is all well and good, but let's get into calculus in physics. There are all kinds of wonderful ways that calculus comes up in physics. So let's first give a simple example. We've seen this idea, but I want to remind you that if you have a graph of velocity versus time, let's say time's in seconds and velocity is in meters per second, and we have this baboon, and over the period of 4 seconds, that baboon starts with a velocity, I'll put it in blue for you, the velocity is 0, and then it goes up to some value, stays there for a little bit, and so we say the baboon went 20 meters. Yo, that's an easy problem, but we don't know where the baboon is. That's that initial conditions that we don't know. All we know is that it was displaced. So maybe we should change this to say the baboon was displaced by 20 meters. Yo, okay, so that's great. Well, we also know that change in velocity is the integral of acceleration over time. So we could do a problem that shows that. For instance, I could have a rocket, and the rocket might have an acceleration graph that looks like this.